Bright QT. Every student matters.
Hello dear students, today we'll be talking about the heating effects of current. In this chapter electricity, till now we have seen and studied about current, right? The flow of electrons, how we combine the resistances in series and parallel, and the details regarding that. Now we'll be studying about the other effect that is produced by current. It is a common observation that we have seen that whenever we light a bulb or an electrical appliance, we observe that it becomes hot. Now, from where does that heat comes? Fine. It is just when the current is switched on, only then they become hot. Otherwise, they are not. That simply means that current may also produce heating effect. That is what we are going to study here, right? We have already studied that. We know that potential difference was given by the formula work done upon charge moved, right? This is what we have studied earlier in this particular chapter only. So potential difference was represented by capital V. This is work done upon charge moved represented by capital Q. From here I can very well relate by cross multiplying that work done is equal to potential difference multiplied by charge moved, right? Now this is my equation number 1. I'll just state over here only. Next, I know that current I is also equal to Q upon T. Fine, this is the formula that we have studied about current. From here, if I relate what exactly Q is equal to, Q will be equal to, by cross multiplying, I'll get I multiply by T. So, this is my second equation that I can relate from here. Fine. Now, putting this value of Q in this above equation number 1, what I'll get is work done is equal to potential difference multiply by, rather than writing Q, I can write I multiply by T. So, this is one formula for work done. I give it equation number 3. Now, I know that as per Ohm's law, V is equal to IR. So, if I replace the value of V with IR, now my equation number 3, that is this above equation, becomes work done is equal to, now instead of writing V, I am writing IR multiply by I into T, as it is I am writing, right? So, what I get here is work done is equal to I into I can write I square and R into T. This is the formula for work done. Now students, there was a law that is known as Joule's law of heating. This Joule's law of heating performed by Joule stated that work done is equal to heat produced. Whatever the amount of work you are doing, the same amount of heat will be produced because heat is a form of energy, right? So, because of this Joule's law of heating, I can replace work done with heat produced. So, the same equation I can relate with heat produced is equal to I square RT. Now, this is the actual equation that we will be using in our numericals, that H, which is heat produced, is equal to I square RT. H is the heat produced, I, as we know, is the current, R is the resistance, and T is the time. Got it? Now, looking at this formula, I can easily relate that this heat which is produced, it depends on various factors. What are those factors? In the formula, we have these 3 things. So, these are the factors on which the value of heat will be dependent. First factor is the amount of current. Second factor is the resistance of the wire or the substance used, and third is the time. And according to this formula, what exactly is the relation? Heat produced is directly proportional to the square of the current. Heat produced is directly proportional to the resistance and heat produced is directly proportional to the amount of time for which current will be passed. Got it? So if I want to increase the amount of heat energy produced by current, I can opt for these three options. Either I can increase the amount of current. If I increase the amount of current, the heat will be increased square of that effect. For example, if I double the amount of current, then the heat produced will be 4 times. Or if I triple the amount of current, then the square effect, 9 times more heat energy will be produced. Similarly, if I increase the resistance, more amount of heat will be generated. If I increase the amount of time for which current is passed, more heat will be generated. Fine, got it? Now there is one important thing that we need to remember over here. There are so many times the question arises that if we switch on the bulb or an electric iron for that matter, we see that the electric iron, that is the press or the bulb, it becomes hot, but the cord does not. Why is it so? The cord should also become hot, we should also feel the heat, but it is not the case. Reason, of course, the amount of current is going through it, the time is also there, but the resistance of the cord wire is basically a metallic wire, right? So that metallic wire has a very low resistance, right? And another thing, that metal wire, we cannot touch it directly, so that is coated with some insulators like PVC, right? That is what we see, the type of plastic that is above the metal wire which is inside it. So because of that, it does not glow or it does not become hot. Fine. So this is the relation, and for this we need to specify Joule's law of heating. Why? Because work done is equal to heat produced. That is only because of Joule's law of heating. We need to specify it while we will be deriving this formula. Got it? So this is the heat produced during the current